Hello, welcome everyone. Let me just check I'm just going to check the share status. The recording started. Hello, everyone. Thanks for joining us for today's webinar. My name is Jeremy Heenek, and I'll be your host today alongside David Wiseman, who will be doing the bulk of the presentation. David's going on a couple decades of handling support, doing training, and helping with the development of this software. So I look forward to seeing how he breaks down and builds this model. We're excited to have you here today. The topic is how to build a fault tree model from a schematic to help improve your model-based system engineering models. Here's what you can expect during the meeting. We'll start with a brief introduction to the IEC 61508. Then we'll dive into the step-by-step process of building the fault tree model from a schematic, which includes David introducing the schematic. During the meeting, we will be fielding questions. So it's an interactive meeting. Myself, Rachel, and Brett will be answering questions via the chat menu. Brett is over business development in the Americas, and Rachel is over sales in the EMEA region. We do have a lot of people in this meeting, maybe more people than we've ever had in a meeting. So be patient with us. We'll industry-specific questions, or we may not be able to get to everybody's questions, but all your questions will be answered, even if it's in the email file follow-up. And to end up, we'll give you a sneak peek of our next webinar. Hopefully this is a series. We're trying to create a community of our users where we can share information and deal with topics that you might find interesting. So just to get started, the IEC 61508, it's really a best practices standard that's been widely adopted. There's many different standards depending on the vertical or industry you might be in. We have the 61511 that's tailored to the process industry, the ISO 26262 that's specific to automotive, the ARP standard, which is specific to aerospace, but there's many children of the 61508 standard. So even if yours isn't listed here, there is a good chance we cover the quantitative portions of all of the children's standards to the 61508. All these standards share common themes, like the 61508 uses SILs or SIS, which is system integrity levels or safety instrumented systems. For automotive, they have some automotive specific nomenclature, like they'll call it an ASIL, which is an automotive SIL, but we're still handling all of those quantitative portions. All the standards have a life cycle approach. They go all the way from design through decommissioning. There's sections of the standard that deal with risk-based decision making. This is where Isograph would step in and help you make decisions based on system failures. And then, of course, the verification and validation portions, where you ensure the system meets a certain safety requirement, and you can use Isograph for those sections as well to help redesign systems. But without further ado, let me pass this over to David, and we'll get started on the presentation portion, the software presentation portion of the meeting.
Yeah, thanks very much, Jeremy. Hi, welcome everybody. So yeah, today we're going to be taking a look at building a functional safety fault tree and reliability workbench based from fairly simple schematic. So I'm going to begin by showing you that. We'll take a look at our schematic. Hopefully you should be able to see that now. So the concept of a safety instrumented system is probably going to be familiar to a lot of people in the room. This is a pretty straightforward example of that. Now, up front, this is of course very much a kind of process-centric example. You have pressure sensors, you have valves and things like that. These ideas, of course, translate to safety systems across a variety of types of system. So, here where we're looking at pressure sensors and valves, you could just as easily be looking at impact sensors and an airbag system, or heat sensors and a fire protection system. Same principles apply to different systems. And as Jeremy was kind of talking about earlier, all of this kind of originates with IEC 61508. So whether you're dealing with, process industry, IEC 61511, or aerospace ARP 4754, or automotive ISO 26262, a lot of these ideas are going to be the same. So if you're not from the process sector, you can use a little bit of imagination, and this hopefully will still be very useful to see how this proceeds. But let's walk through this example a little. So what I have is something, could be water or oil or something passing through a pipeline. And I have an array, 3 sensors, 3 pressure transmitters watching the pressure in that pipe. And they're there to detect overpressure, let's say. And I have here a logic solver. This logic solver is looking for a signal of overpressure from any 2 or more of these sensors. So you can see there 2 out of 3. In the event that 2 or more of my sensors pick up a problem in that pipeline, it's going to trigger the shutoff valves, these block valves, to close. So this is your classic sensors, logic solver, final element type example, where you have your sensors, the pressure sensors in this case, your logic solver, and here our final element is going to be the block valve. But as I said earlier, your final element could just as easily be the charge that sets off to trigger an airbag, or it could be what's the word? Smoke detector that maybe triggers, sorry, not the smoke detector, the sprinkler head that's triggered by the smoke detector. So like I say, this principle translates across a lot of different types of system. But we need to look at a fault tree for this system. And of course, a fault tree is always looking for maybe a failure of that system or a hazardous scenario arising in that system. In our case, it might be, a failure to, say, trigger the final elements. The system is no longer going to respond on demand. We're in a dangerous failed state where if an overpressure were to occur, we would not be able to respond to that because some aspect of our system is not working. So let's jump to reliability workbench. So maybe many people in the room are already familiar with reliability workbench, but I will just give a few words to what this is, just in case anyone isn't familiar. So reliability workbench, it's a desktop application with modules in it for different types of reliability analysis. Today, of course, we're focusing on FaultTree. So that's going to be our main concern. We're going to be building a fault tree for our system. And of course, when you build a fault tree, there must be people in the room who've been on our fault tree training course. I'd be very surprised if there isn't. You may remember that idea of building a fault tree from the top down, where you identify the hazard and then you begin to identify the intermediate causes of that hazard before terminating with the basic events. For a functional safety system like this one, it is no different. It works exactly the same way. Fault trees across the board, across industries, work basically the same way. So we begin by identifying what's our hazard, what's our dangerous failure. So I'm going to go to add, I'm going to add a new top gate, and that top gate will represent that dangerous failure state of the system. So I'm going to add that top gate, and I will double click on that, and I can pop in a description. Now this is, I'll call it HIPPS, so it's a high integrity pressure protection system that I'm modeling here. So I'll give it that name. Let's call it, for brevity, I'll just say high integrity pressure protection system failed. So keep that simple. That is going to be my top event. So it's in a failed state. I'm in a dangerous failed state where, if there were an overpressure in my system, I would not be able to respond to that problem. Before I go any further, what we don't want is to be jumping backwards and forwards between the software and the image. So what I'll do is I'll show you a little feature which maybe you've used or seen and not had a chance to try yourself. I'm going to add what we call a bitmap object, and I'm basically going to display that schematic in my FaultTree diagram, because that is going to make my life a lot easier, and it might also prove useful if you ever have to do this yourself. So I'm going to create this schematic object, and I am going to link that to my schematic file, which is a PNG, if I remember. There it is. Open and click OK. So there's my schematic, and I can display that in a label in my project. So I'll add a label, which is, let's see where, I'm blanking on where that is in here. Oh, there it is. Add a label, and I will simply drag and drop that into there. And there is my schematic. That's going to make my life easier, so I don't have to jump backwards and forwards between windows. So, okay, back to our FaultTree. Top gate, our safety system is in a dangerous fail state. Why would that happen? So there are basically three fundamental elements to our safety system: the sensors, the logic solver, and the final elements. If any one of those three aspects of our system were to fail, we would not be able to respond to an overpressure. Any one of those three problems would result in a dangerous failed state for our system. So I'm going to add objects beneath my top gate to represent those problems. So I will add a gate to the diagram, and I will just left click on my top gate, 1, 2, 3, to create those objects. Right click and clear, that's just going to take me back to the regular cursor again. So I now have these three gates beneath my top gates. Now notice that that is all logic. Basically what that means is I would have this failure if any one of these problems were to occur. What are these problems? Well, let's say that's no signal from sensors. Let's call it fail to detect high pressure. And I'm just going to call that sensors. So that's a problem with my sensors. That's one thing that would result in a dangerous failure. This one, failure of the logic solver. Let's call that logic. And I'll say that's logic solver fails. And what's the other problem? Okay, that would be valve. I would call that, say, valves fail to close, and we'll just call that valves. Okay, so those are the three problems that are going to result in the loss of our HIPS system: loss of the sensors, loss of the logic solver, or the valves failing to close. And again, in that typical FaultTree way, we then ask, well, why would that happen? Why would we not be able to detect high pressure in that valve? Well, we've got these three sensors, call them pressure transmitters. If we get a signal from two of them, then that's going to be enough to trip the system and cause the valves to close. which means that if any two of them were to fail, leaving us with only one functioning sensor, we'd no longer be able to pick up a high pressure event in that pipe. Any two of three failures would result in a failure of that sensor array, result in it being unable to pick up a problem. Now, I can't break that down any further. I'm not going to go down to the individual bits and pieces that make up a sensor. There'd be no point in me doing that. I probably don't have the failure data for the individual bits of a sensor anyway. So I'm going to add 3 events, each one representing the failure of one of my pressure transmitters. So I will just left click, 1, 2, 3, right click and clear to create those 3 sensor events. So I'm going to rename them. I won't worry too much about the description for now. I'll just call that pressure transmitter 1, pressure transmitter 2, and pressure transmitter 3. So that's only half the story there, because we've got those 3 sensor events. Each one represents the failure of one of our pressure transmitters, but we said there would be a problem if 2 or more of those 3 sensors were to fail. How do we express that? In the fault tree, we do it by using a vote gate. So remember, our top gate is an OR gate where any one or more of the failures below it would cause that problem. A vote gate is M out of N. If M out of N inputs fail, it results in a failure of the gate. So I'm going to pop back into that gate. I'm going to make it a vote gate. And as luck would have it, the default vote number is already 2. So I'll leave that as it is. We have a vote number of 2. Click OK. Now you see we've got 2 out of 3 vote gate. That gate is in a failed state if any 2 or more of the events beneath it are failed. So that covers the pressure transmitters. That covers our sensor array. What about the logic solver? Well, it might be that we can't really break this down further. The logic solver is a single element in our system. Maybe it's just supplied to us by a manufacturer, and they've given me a nice data sheet for that logic solver saying, this is the estimated failure rate, or this is the estimated MTTF of this bit of kit. So actually, I can't break that down any further because I've got a bit of a problem now because I've already created a gate. And I might actually want for that to be a basic event. I can't go any further than that. I can't break that down further. So really, this should be an event, not a gate. So can I easily rectify that? Well, we can just select that gate. Then we can right click on it. And I'm going to make that an event. Gate to event, event to gate. I can just flip one type of object to being the other type. Turn that gate into an event. Simple. Now I've got a basic event representing the failure of the logic solver. And last but not least, we have the final elements, our block valves. Now, this is where I'd like to talk a little bit about, I guess, the pitfalls of translating a schematic into a logic diagram. This happens a lot with RBD, reliability block diagrams in particular, but it can happen with fault trees too. People tend to think, when they look at, say, a system, they see maybe 2 things arranged in parallel. Let's say, you've got here sensor, sensor, sensor. They appear to be parallel to each other, so that might make you think, well, AND logic, vote logic. Parallel means AND. Conversely, series means OR. You see this a lot, particularly in IEC 61508, where the logic in a safety system is very often expressed with reliability block diagrams. Blocks in series, they are 2 out of 2, meaning that both of those things have to work in order for the system to work. And a person might look at this and think, well, block valve 1 and block valve 2 are physically in series, so Maybe the block diagram should be in series. Maybe the logic should be OR logic, because of course, serial logic is the same as OR logic. But you should not be trying to simply translate the architecture of a schematic, the architecture of a system, directly into a fault tree or directly into a reliability block diagram for that matter, because ultimately a fault tree is not meant to be a one-to-one representation of the physical architecture of a system. Just because things are physically in series in a system doesn't mean that the logic is series. It doesn't mean that the logic is OR. It's all about the reliability relationship. It's all about the functional relationship between these two bits of equipment. So what's actually happening here? Well, my sensors pick up a problem, and the logic solver says, okay, 2 of your sensors are saying there's high pressure in this pipe. We need to shut down. So it sends a signal to block valve 1, and the same signal goes to block valve 2 as well. If block valve 1 closes, great. System is shut down, we've stopped the flow, so we're good. What if block valve 1 fails? Well, if block valve 1 fails, we still have block valve 2. That valve could be closed and on its own could just as easily stop the flow of product through that pipe. So what we're actually saying is that despite the fact that these objects are physically in series, the logical relationship between them, their functional relationship, is parallel, because if you lose one of them, the other one can compensate for that loss. You don't need both of those valves to work. It's 1 out of 2. As long as one valve works, you're okay. You're only in trouble if both valves have failed. For that reason, we'd be looking at using AND logic. So again, this is something I've seen a lot with our training courses, especially when we've dealt with block diagrams, that just because something's in series in your schematic doesn't mean that it's in series in the diagram. You need to think about what the actual logical relationship is, what the reliability relationship is. But with that said, let's pop those events in. I'm going to add events beneath the valve gate. This one here we'll call sort of block 1, so that's block valve 1. I'll call this one block 2, so that's block valve 2. And as we said, only if both of these fail would the final element part of our system be in a failed state, meaning that this should be an AND gate. So I double click on that, and I'll switch that to being an AND gate. So there is our fault tree. In terms of the diagram for this system, this fault tree is now essentially complete. So it's a relatively simple example, but it gives us a nice idea of the different types of logic that we might encounter in a safety system, how they might be represented in a fault tree. So we've got, the overall failure of the system that could be caused by the loss of any part of that safety instrumented system, sensors, logic solvers, or final elements. We would lose the sensors if any M out of N sensors were to fail, in this case 2 out of 3, because we could no longer send a high pressure signal from 2 sensors. We'd only have 1 left. The logic solver, we said, this is pretty simple. That just, if that fails, the system fails. And finally, the final elements, which we said, despite being physically in series, the relationship in terms of redundancy is parallel, because we would only have a problem if both of them were to fail, in which case we've used AND logic. So we will talk in a moment about the quantitative side of fault tree, about entering the numerical data into a fault tree. But I want to talk for a moment about the qualitative side of fault tree, because you may be familiar with fault trees already and maybe know a little bit of this, but again, for anybody who's kind of new to fault tree analysis has both a qualitative and a quantitative side to it. Obviously, there's the quantitative bit that you might think of straight away, the probability calculation. But you also have that qualitative analysis where it's possible to determine from the fault tree what combinations of events, if they were to occur together, would result in a dangerous failure of the system. What combinations of these events would lead to that problem? You can in fact do this analysis of a fault tree without any numerical data at all. And that on its own can be useful even before you started entering numbers into a fault tree. So maybe we'll do a little of that first. I'm going to hop into my project options. I won't talk through this bit too much because I don't want it to sort of turn into a sort of live software manual. But I'm just going to pop into here, into the custom options. I'm going to ask the program essentially to show me the minimal cut sets for this fault tree. Show me the combinations of events that will cause this top event to occur. So that's all I'm doing there, asking the program to show me that information. So I click OK, and I will run the analysis of that tree. And again, remember, I'm doing this with no numerical data at all. So we can do this without entering any numbers. You can see there it's telling me the probability is 0, naturally, because I've not put any numbers in the fault tree just yet. But if we take a look at the results from that fault tree analysis, I can take a look at the sets. You can see there already the program is telling me what combinations of events would lead to a loss of that high integrity pressure protection system. As you might expect, any combination of two sensor failures would lead to a failure. If both of our block valves failed, that would cause a failure. If the logic solver failed, that would cause a failure as well. Now, obviously, this is a very simple fault tree by comparison to many, but even so, you get an idea of how useful this can be, because let's say you've built a huge fault tree, could be hundreds of events and gates, could be thousands of events and gates, but you've not got the numerical data yet to populate that tree. Can you get anything useful out of it? You can, because you might get thousands and thousands of cut sets here. And it would be obviously impractical to read through them all manually, but you get information back like appearance data, a list that shows you how many minimal cut sets each event appears in and what order those cut sets are, how many events there are in each set. This alone can give you an idea of which events could be causing the biggest problems, where you might be able to introduce more redundancy. So if you're seeing events that are appearing across lots of different minimal cut sets, highly dependent events, that alone can be useful information as well. But that's kind of an aside. I did want to just point out that while obviously probabilistic calculations in fault trees are very useful and very important, even without that information, a fault tree can still return useful results. Let's turn our attention now to the numerical side of fault tree, doing a probabilistic calculation. And one of the things we'll need to do is provide failure information for the basic event. So how often do we expect a sensor to fail? How often do we expect a logic solver to fail? Now, in the software, there are many, many types of failure data that you can provide, from simple failure rates and repair rates through to sequential aircraft failure models and viable models for wear out and stuff like that. But keeping on theme with this IEC 61508, safety integrity system model that we're building, I'm going to create a model for my pressure transmitters, for my sensors, that uses the IEC 61508 failure model. So this is going to be a failure model, failure data for a pressure transmitter, and it's going to use the IEC 61508 model. Now you could see there was a list of like 18 different failure models. I always say in the training that most people we'll probably only ever use like maybe 3, 4, 5 of those models, because many of them are quite specialized. And I don't think I've ever seen a tree that used 20, like a 10 or 15 of them. Usually it's stuff like the rate model, the fixed model, dormant model. I'm going to look at the IEC model though, and I'm going to put in a failure rate. Now I'm going to enter all of my information in hours. You can use other units. You can tell the program what units you want to use. I'm going to stick with hours for everything because it's nice and simple. So I'll say the failure rate of a sensor, 10 to the minus 6 approximately. Now, this kind of information can come from a variety of sources. You might get a data sheet from the manufacturer of the sensors, for example, that specifies what the failure rate is. Or you could reference libraries, things like, for example, NPRD 2023, non-electronic parts library, that can actually be used with Reliability Workbench as well. You can pull failure rates from that library. We have a data link manager that allows you to link a Reliability Workbench project to external data like doors or even Plato INS as well. Information can then be pulled from those systems via the data link manager. There are lots of different places this information can come from, lots of different ways of getting it into the program. For the purpose of the demo, of course, I'm doing it by hand. So I'm going to pop in a mean time to repair. Again, just like a pretty short repair time for that. A test interval. How frequently am I doing a proof test? How often am I testing for this problem? Because remember, this is a safety system. Probably not going to be using it all the time. Most of the time, it's going to be in a dormant state. So if it failed, I wouldn't know about it. So I might need to test a little bit like you test the fire alarm in your building, or like you might take your car to the mechanic and they can look for problems that haven't yet manifested. Maybe there's a warning light in your dash that doesn't work anymore. You just don't know yet because that problem that triggers that light hasn't occurred. So we need to test for those problems. I'm going to put in a proof test interval for that. I can specify what percentage of those failures are dangerous. I can specify what percentage of dangerous failures are immediately detectable, where the rest must be picked up by the test. Same for safe failures. I'll say safe failures. I can't detect any of them. I have to do an inspection to find those. Proof test coverage. What percentage of dormant failures, what percentage of undetectable failures cannot even be detected by can be detected by the proof test? In this case, it means that 10% of hidden failures are not picked up by the proof test either, in which case I have to go to overhaul, meaning like every, let's call it 5 years or so, I have to do an overhaul of my system, and that's where I might be able to pick out any problems that escaped my standard proof testing. Now, this information can be entered as you see it here. There is a little button at the bottom here as well, our IEC 61508 calculator. This is useful in situations where maybe the manufacturer of your sensors has given you a data sheet, but instead of giving you percentages for coverage and stuff like that, they've just given you the dangerous detected failure rate, the dangerous undetected failure rate, and so on. So all those failure rates are just given to you on a piece of paper. You can put them in here and essentially backwards calculate those numbers from those rates. I will click OK. That creates that model. You can see it just here. And I can simply drag and drop that and say, I want all 3 of those events to use that same model. And those events remain independent of each other. They still represent the failure of separate sensors. It's just now they all use the same data. And if I update that data, all of my sensors will be updated with the new information. Okay, so at this point, I'm sure everybody is very excited to watch me spend the next 5 minutes typing numbers into boxes. But in the interest of time, I'm going to do it a different way. So I'm sorry to disappoint you. There is a feature, again, if you've used the software before, you've probably come across it, the library feature that allows you to pull information from one project into another. And basically what I've done is cheat a little bit and set up the rest of my failure data in another project, and I can just easily copy it over. So I'm going to go to File, and I'm going to attach a library, and it is in here. There it is. That's just my project that contains the other data I want. And there you can see I've got models set up for my logic solver and for my valves. So I'm just going to bring those in. This feature is really handy because it allows you to copy not just failure data, as I've done here, but basically anything from one fault tree to another, whether it's failure data or viable data or bitmaps or even chunks of other fault trees. You can copy pages of fault trees from one model to another. This is useful if you want to sort of set up a library of commonly used fault tree architectures. So there might be like little things like the valve vote, sorry, the sensor vote that we set up that we always use across all our fault trees. Well, I don't want to waste time repeating that work over and over again. So I just refer to my library, grab the chunk of fault tree I want, pull it over. It will bring with it any failure data or anything else that's already attached to it in the library. I'm using this in quite a simple way, just grabbing the failure data only. I'm going to pop that guy onto the logic solver and this one onto my 2 block valves. So we're getting there. We're getting close to being able to model this fault tree now. But there are a couple of other little bits I'd like to talk about. Obviously, in safety systems, we are very, very concerned with the concept of common cause failure. There is always that possibility that several otherwise independent components might fail at the same time for the same reason. For example, maybe an impact might cause 2 or 3 of your sensors to fail at the same time. Maybe a power surge might cause several electronic components to fail simultaneously. Components that normally would fail independently of each other could all go down at the same time because of one problem. Now, there are different ways to model that in a fault tree, but again, keeping on theme with IEC 61508 and its associated standards, I'm going to take an analytical approach and use a beta factor model. So I will add a common cause failure model, and this model is going to represent the possibility that my pressure transmitters all fail at the same time for the same reason. Could be because the person doing the maintenance of my sensors doesn't know what they're doing and I need to train them properly, and they've made the same mistake with all my sensors. Could be that they all came from the same manufacturing batch and they all have the same fault. So there's any number of reasons a common cause failure could occur. We can model that here with a CCF model. So I'm going to call that ET-CCF. So that's a pressure transmitter common cause failure. I can put in a beta value that indicates what proportion of failures come about due to common causes. Now, while I won't go into depth on this, you'll notice there is an IEC 61508 option. IEC 61508, specifically, I think, an appendix in part 6, has a kind of questionnaire that you can run through where you answer questions about your sensors and your final elements and so on. And when you get to the end, based on the answers you've given, you can calculate what the common cause failure beta factor should be. We've basically put that into code so you can turn that on, go through all of those options, and when you've selected all your options, the program gives you the common cause failure factor based on that. I might even keep that actually because it's the same as the value I want to use. So you could enter the value manually, or if you're following 61508, you can go through that process of selecting options and the program will estimate a beta factor for you based on that formalism set out in 61508. So I'm going to say that basically 5% of pressure transmitter failures actually affect all three sensors at the same time. So I'll click OK. And I'm going to say all three of these events are affected by that same common cause. Now I want to do the same for my block valves, but again, I have that in my library already. So I'm going to grab the valve common cause failure model that I set up previously, pop that into my model, and I'm just going to attach that to those two. So there's a possibility that these three events might all fail simultaneously, and there's a possibility that these two might fail simultaneously, again with that 5% beta factor. So what else is possible here? Let's think again a little bit about IEC 61508. This is now getting into the weeds a little bit with regards to 61508, because one of the other things you can do in the program is ask it to calculate the hardware fault tolerance in your fault tree as well. Basically, the number of hardware faults that your program that your system can take based on the probability of failure of the individual pieces of hardware and the quality of that hardware. You might have noticed there is a type option in the 61508 model, type A and type B. This refers to a table, if I remember, it's in part 2 of IEC 61508, where you can estimate hardware fault tolerances based on the safe failure fraction for the piece of hardware and basically the quality or how well you know that system, how well understood it is. A is the best, B, not, you don't know it quite so well. And in order to calculate then the hardware fault tolerance, you need to set a SIL target, safety integrity level target. This can be done for the top gate in your fault tree. So I can go in here, go to the IEC 61508 tab and say that the SIL requirement is maybe, let's say it's 2, for example, and click OK. So obviously we won't see anything yet. We haven't yet run an analysis of this fault tree. Before we do that, there's just a couple more options that I'd like to set up. I'm going to go back into my project options. I'm going to head over to the calculation tab because I want to do two things. Number one, tell the program what is the lifetime of this system. This is going to be important, I think, particularly when you're dealing with repairable and non-repairable parts. For dormant failures, because of the way the mathematics works out, this tends not to be as important. But if you are dealing with repairable failures or non-repairable failures in particular, system lifetime can be important. Now, again, I'm working in hours, so I'm going to set that to, that is going to be 20 years in hours. One other thing I will do is switch my dormant failure model option to 61508. I'll try not to spend too much time explaining this, but basically, IEC 61508 handles dormant failures in a way different from a conventional fault tree. If multiple dormant failures happen at the same time, the way that IEC 61508 calculates the probability of that is actually slightly more pessimistic than your average fault tree calculation. So that's why we have this option. It basically asks the program to use an algorithm that's more consistent with 61508. And I will also ask the program to show me the hardware fault tolerance when it does the calculation. I'll click OK. There's nothing really left but for me to actually run an analysis of this fault tree. We already did that once, and we got the qualitative results from our fault tree, the minimal cut sets, the combinations of events that would lead to a failure of this system. But now we have the data in there to do a quantitative analysis as well. So let's run. And it's pretty quick, as you can see. So a couple of numbers I'll point out here. I'm going to go into the results proper in a moment. I'll point out here, you've got unavailability, or in the parlance of functional safety, the probability of failure on demand. So that's your PFD. What's the probability that if you ask this safety system to work, it doesn't? What's the probability that when you make a demand on this system, it is not going to work? That's coming out at about 0.0047 based on the numerical data we entered at the bottom. You'll notice also that for each gate, the program is showing a hardware fault tolerance that is based on your SIL target, the safe failure fractions of the individual events, and of course, the type of failure. Is it well understood or is it not so well understood? But let's dig into the results a little bit again. So I'm going to go back to the results and take a look at the summary. So we've got probability of failure on demand, probability of failure per hour. Now, which of these two you look at will depend on the nature of the system that you're looking at. A low demand system like this one, where you're only asking it to work occasionally, PFD, probability of failure on demand, is going to be more important. Something that you use a lot, a high demand system, maybe something that runs continuously, you might be more interested in PFH, probability of failure per hour. We looked at the cut sets earlier. We saw, what combinations of events would cause a problem. Notice now that we also see the common cause failures popping up in there as well. We didn't see those earlier because we hadn't added them yet, but the program is treating those as events that could also cause a failure. Of course, if there was a common failure of both of our block valves, that would cause a failure of our system. So that on its own is a single point of failure. But I'd also like to take a look at importance. This is useful for pinpointing which events in your system have the potential to cause the biggest problems. So here, for example, I've got my common cause failure for valves, and that has a comparatively high Fussell-Vaselli importance. It's basically indicating that this failure is contributing to about 44% of failures of this system. You can basically say if something has a high Fussell-Vaselli importance, it's having a big contribution, or at least relatively large contribution compared to other events. Similarly, the block valves individually have quite a high contribution. After that, other events kind of drop away. So these seem to be the big contributors. But you also have Birnbaum importance. That's useful too, because in your system architecture, this is telling you which events your system is most sensitive to. So this is saying, well, if you can improve that in your system, if you can improve that common cause failure situation, you will get a pretty big improvement in your system. What this is then telling you, this high Birnbaum importance, is that if you let this get worse, then your system is going to deteriorate very quickly as well. So you can think of Fussell-Vaselli as giving you an idea of how much better your system could be if you made that event better, maybe added redundancy or bought better parts. Whereas Birnbaum importance is saying, well, if you neglect this event, if you don't maintain this component properly, if you let the failure rate get worse, your system is going to suffer a lot more for that. So you can see it's very sensitive to the common cause failure, whereas it's not as sensitive comparatively to the individual block valves. So these numbers are helping you to understand where the weaknesses are in a system, but also where the opportunities are for improving that system as well. So That's it, really. We have, starting with our schematic and our understanding of the way this safety system is supposed to work, we've built a fault tree diagram using that top-down method of saying, well, if this is the event we want to learn about, this dangerous failure of our safety system, what would be the direct causes of that problem? We identify those causes. Where possible, identify the causes of those problems. And once we've got to the bottom of the fault tree, we terminate with basic events, the most fundamental events about which we plausibly could have information. We populated that with information about how frequently we expect those failures to occur and how detectable they are, information about the common cause failures as well. And from this, when we've run the analysis, we've learned not just how likely it is the system is to fail or how frequently it will fail, but also it feeds back because we can go back and say, well, okay, the architecture as it is now, we can see there's room for improvement here. We've got problems with the common cause failures in our check valves, it looks like. So if we can resolve that problem, then we're going to have a pretty substantial improvement. We could introduce more redundancy, we could improve our maintenance, we could do something to avoid these common cause failures and improve the reliability of the system. So yeah, it's not just about learning how bad things are. It's not just about learning how where how much of a problem we have. It's also about looking for the opportunities for improvement. And that's what we can get then from doing things like an importance analysis and a sensitivity analysis. Yeah, that is the end of my presentation on how to build a functional safety fault tree just based on a simple schematic. And I think we have some time left for questions. So, Jeremy, I think you were going to have a look through and see if we had any interesting questions come up.
Yeah, there is a lot there. Could you just give us really quick and show us what we can use as data sources to the FaultTree projects?
Yeah, so there are different places that data can come from. I mentioned a couple of them earlier. For example, hopefully this will pop up for me. It might take a moment to load. You can get parts libraries, things like, for example, NPRD. This is the non-electronic parts library that's published by the Quanterion Corporation, and it contains a long list of mechanical and electromechanical parts with failure rates that have been collected from the field. So you can see there it can be things like sensors, sensor arrays, and so on. Things like valves, different types of valves. So you can find the type of valve you need, and you can see there it provides a failure rate. In this instance, it's in failures per million hours. But you can basically drag and drop that then into the program. You can then change what model you want to use for that. If you then want to change the IEC and then enter the additional information. Other sources, of course, are the manufacturers themselves. A lot of hardware manufacturers might provide a data sheet with an estimate of MTTF, mean time to failure, or failure rate, or even for things like final elements and sensors, you might even find some that provide the sort of IEC style failure rates, detected, undetected, dangerous, and safe, which, as we saw, can also be fed into the program. And well, if you're lucky or if you've been working really hard for the past few years and you've been meticulously collecting failure data from your own system, that too can be used as part of your model. For example, in Reliability Workbench, along with FaultTree, there is a Viable tool. This allows you to import your own historical failure data into your model, do a statistical analysis of those past failures to get an estimate of, say, MTTF or even wear out parameters. And that can then be fed back into the fault tree. So in fact, the events in your fault tree, their failure rates are based on real failures that you've seen in the real world. making your fault tree more representative of your own system. Now, obviously, that's a luxury if you have that kind of data, but it's another option that you have. And kind of as we alluded to, you can even build your own libraries. You could build a library of data based on your own observations or manufacturer's data sheets, just for easy reference later as you're building your fault tree. I think I mentioned also earlier that there is the data link manager. That is a kind of intermediary tool that communicates between reliability workbench project files and external sources of data, most commonly DAWs and Jammer for requirements management, and more recently, Plateau Eins, which is, amongst other things, a FMEA tool. So there's information there that can be pulled into the software as well. So yeah, there are a wide range of options for where this information can come from.
David, can you take just a really quick example of the reporting capabilities on this tree?
Certainly, yeah. So obviously, once you've built a fault tree and analyzed it, one of the things you're going to want to do is pull that information out in a format that you can share with colleagues, with management, with clients, people who themselves may not necessarily have access to the software. I'm going to hop into reports, and again, because I don't want to spend a huge amount of time then demoing the reporting, give you a high level overview. This works by allowing you to open one or more report templates that will automatically populate with data from your project. And you can create your own reports as well, or you can just use the ones that we provide. I'm just going to show a couple of examples. So classic one, of course, would be the fault tree itself. So there is my fault tree. You can see it's even showing the schematic alongside it. You can see it's a little bit small, so I might want to go into my reporting options and maybe change the orientation so that it's landscape instead of portrait. I could do that if I wanted to. That report can then be printed off or dumped into Word or PDF. Similarly, you can produce plots this way. If you wanted a graph of that importance data we were looking at earlier. Or simply, you might want like a list of your minimal cut sets. So that's a pretty common report that people tend to output from the program. Just a list of your cut sets with their probabilistic data. So those are just a couple of little examples, all of which can be exported into other formats if you need then to attach that to an email and shunt it off to whoever needs to see it. And they're all just customizable.
Perfect. Thank you, David. Let me just share. There is a lot of questions. I'm going to post something into the chat menu really quick. So thank you for that presentation, David. There were actually several questions that teed up the next webinar, and that is using the fault tree analysis tool uses Boolean algebra to figure out the probability of the top gate failures. However, there is we do offer another tool that's as mature as our FaultTree Plus software. And so with analytical methods, you have a hard time handling things like spares, rotating equipment, maintenance, capacity throughput, things like that. However, you can apply a different type of mathematics, which would be a Monte Carlo simulation tool or generator. And it's a random number generator, and it opens up the window to these other types of calculations. So that's actually the topic of our next webinar. It turns out we're very busy around here in October, so this webinar had to get pushed out to early November. But I've put the link to the webinar in the chat menu. If you're interested in this topic, even if you don't go down this road, it's a really interesting idea of how you can apply different mathematics and get different outcomes. The availability workbench will be kind of the topic of the next webinar. This webinar, actually, we should have cut it off at some point. It completely filled up. So if you are interested, please sign up for the next webinar. And then just in conclusion, it would be nice to hear any feedback from any of you attending the webinar. There were a lot of questions we weren't able to get to. Most of them are questions on, what kind of logic was used at the top gate, or different options that maybe we didn't have time to go to in the web meeting. We will follow up on all those questions with you individually. If you have any ideas for future meetings, please send them to me. I've already gotten quite a few really good ideas for future meetings, but we can talk about and present anything you would like in the software. And then when I'll reach out to each of you after the meeting and see if you have any additional questions. You can always access our website for downloads. We're now part of the Peak Avenue group, which has opened up a lot of other offerings that we have as a company. That QR code takes you to the Peak Avenue website and LinkedIn profiles. If you need anything, just let us know. I do appreciate you attending today's meeting. It's been a very popular meeting, and we've been excited to show this to you. Thank you for your work, David. I appreciate everything you did with this meeting.
Not at all. My pleasure. Thanks for helping to organize everything.
Thank you. Have a good day, everybody.
Bye, everybody.